what happens when a particle enters a magnetic field with some initial velocity? Well, this is going to end up being very similar to what happens to the electrons in the wire when we did F-Bill. Okay, except we're going to now use a formula for charged particles, which is F equals BV Q. Okay, and I just want to point something out here, that if we look at IL and we look at the units, I would be amps, but amps are just coulombs per second, and L is meters, so we'd have coulomb meters per second. Well, in the B equals, or the BVQ formula, V is in meters per second, and Q, which is for charge, is coulombs. So the coulomb meters per second is the same as a meter per second coulomb. So the units are the same, and we get, in both cases, a force. So let's take a look at the first situation. We have a proton about to enter a magnetic field, and the magnetic field is represented by these X's, and we're going to again use the hand rule. I'm just going to make a distinction before I show you the hand rule. So the proton is very similar to the positive flow of current in a wire. If you think about it, current in a wire is just coulombs going by, coulombs going some length over time. And even though the proton is the tiniest amount of coulombs we can get, 1.6 times 10 to the negative 19, it still represents coulombs over time. So when we use a proton, we're going to use the same right-hand rule, the in-your-face disgrace rule, that we used for the force on a wire, which was the right-hand rule. But if we have an electron instead, the electron is negative, and so we're just going to use the same hand rule. We're just going to use the left hand instead. I usually do it this way to show you that there is an electron in the word left. The distinction is that a proton is very similar to the positive flow of current, right? Because a current is coulombs going by. Well, we have part of a coulomb. We have the tiniest, 1.6 times 10 to the negative 19, a tiny, tiny amount of coulombs, but we do have coulombs per second when a proton is entering the field. This is a depiction of a magnetic field. The X's mean that on the other side of this brown wall somewhere is the south pole of a magnet. And behind me, where I'm manipulating this ground ginger to be a proton in this case, behind me somewhere is the north end of a magnet. Now, because this is a proton, as the proton enters the magnetic field, the proton's motion will change because of the force. Now, the force will only exist when the proton is in the field. So until it gets in the field, it's just going to be moving straight. When it gets to the field, now we have the conditions for a magnetic force. I'm going to use my right hand because my right hand is involving positive flow of current. Okay, so my fingers are going to go into the wall or into the screen because the field lines are going into the screen. And my thumb is going to go in the direction that the proton is going. This means when the proton gets to the field, I'm going to be pushing upward on it, which will deflect it, and it'll continue to do that. We'll have circular motion deflecting this. Once it leaves the field, it'll keep going in a straight line. It's only deflected while it's in the field. What if this proton was actually an electron? Then I would use the left-hand rule. Same thing, it's a little harder to show, but I will put my fingers going into the board, and my thumb will go in the direction of initial travel of the electron. So this time when the electron gets in, I'm going to be slapping down on it, so the electron would have this kind of a shape of trajectory. It'd come in and would do projectile motion downward. So summarizing on the template, the proton would have experienced circular motion going into the magnetic field. And the electron would also experience circular motion, but in this case downward. And after the field, it would keep its motion straight. Let's do a quick problem. A beam of electrons travels at 3 times 10 to the 10 to the 6th meters per second. Just to give you an idea of how fast that is, it's just 100 times less than the speed of light. But that would be moving through a uniform magnetic field of 4 times 10 to the negative 2 teslas at right angles to the field as shown. What is the magnitude and direction? So it's a vector, magnitude and direction of the force acting on each electron. Okay, so let's actually address the direction first. And I invite you to do this at home, but using your left hand, this time your fingers would come out of the board or out of the screen for this whole magnetic field right here. And with your thumb pointing in the direction, you would see that the electron would do like the proton did above. The electron will experience circular motion up as it goes through the field. So that's the direction, and the force would equal BVQ. And just substituting the number, so B is the magnitude of the field, which is 4.0 times 10 to the negative 2 teslas. But if you remember, a Tesla is a Newton per amp meter. And then it's going to be multiplied by the velocity, which is 3.0 times 10 to the 6th meters per second times the charge. Now the charge here is the charge of one electron, which is 1.6 times 10 to the negative 19 coulombs. So the coulombs per second is essentially what an amp is. So that cancels the amps. The meters cancel with the meters. And we're left with newtons, which is what we want. And just doing the math here, it looks like we have 1.92 times 10 to the negative 14 newtons, which is a tiny force, but the electron has such little mass that it's very easy to accelerate and manipulate an electron, which is why magnetic fields are a great way of doing that. This last problem was really designed to be an AP problem where students needed to break the velocity into components. But we're just going to look at it for today as just a direction diagram thing. So if you had a proton that was coming into a magnetic field that looked like this, which means north at the top of the page, south at the bottom of the page, I would invite you to use your right hand rule, and your fingers would be pointing down like the arrows, and your thumb would be pointing to the right like this arrow, and that means the force would be going into the screen. And maybe you could depict that somehow like this. Maybe you could say that the proton is getting tinier and tinier. So the direction of the proton would be into the screen because the force would be into the screen. So summarizing on the